Okay, the purpose of this introduction podcast is to just run through some of the basics regarding notation and terminology with respect to vectors. So let's give it a go. A lot of what you see here will show up in context as we go along. A vector is something that describes another way to represent a point in two-dimensional space. We know traditionally within the Cartesian plane that relative to x and y, that the Cartesian coordinate point 3, 4 looks like what you see here over 3 and x up 4 and y. Well, what we can do is we can talk in terms of, well, relative to some starting point, some origin, namely O, we can say with respect to that beginning point, or quite literally that tail, there's a head of a vector that's over 3 up 4. So we can start describing vector OA, and you can see this vector representational form indicating that the tail or the starting point of the vector is, in this case, the origin. That's not always going to be the case. And the head is out here at A. So that's one representational form. And lowercase a, either with a hat or just plain bold, is also another way to represent vector 3, 4 in space in what looks like a column vector form. Well, the column vectors can be pulled apart as 3 times this particular specific column vector plus 4 times this one here, because 3 times the 1 is just going to give you the 3, and of course 0 will account for this will be 3, 0 plus 0, 4, same vector resulting. And these two vectors, namely vector I and vector j, those are so-called unit vectors where I is coming over 1 in x and it's 0 in y, so it doesn't move up or down. That's what that vector is. And then that's a horizontal unit vector, and the vertical unit vector is 0, 1 when it comes to no movement in either way in x, but just 1 up, 1 in y. And we see highlighted in red, there will be a third dimension added. So once we go into the so-called x, y, and then z coming at me or going into the whiteboard here, that's going to be three-dimensional space, and we'll see that there's a third vector, unit vector for that as well. So let's start to just play around a little bit more with terminology. A position vector is a very specific vector that's actually anchored right at the origin. So this vector here of 3, 4, I could grab it and move it to other places. I could start right here, and I could go over 3 and up 4 and have another vector that would not be a position vector. What makes it a position vector is it's anchored right at O, namely the origin. So we've seen all of this before. So we can start to move in different directions with vectors. So instead of going from O over 3 and up 4 to get to A, we can do the opposite. We can work from A to go to O. Well, how do you go from A to O? Well, that just says go over 3, sort of negative 3 left with respect to x, and drop down 4. And so basically going from A to O is just the opposite of going from O to A, and the opposite of that vector is exactly the negative 3, negative 4 that I just described. We can also multiply a vector by what's called a scalar. A scalar is just a single numerical value. So if you were to double the vector, and we're over now at 6, 8, so that would say go over 6, so there's 6 right there, and go up 8, well, that's twice the 4, so you get this vector here that's 6, 8 in terms of where it is positionally in space. Well, in fact, you've just doubled the magnitude or doubled the length of that vector right there. Importantly, if one vector is actually the multiple by a scalar of another, that's actually going to be a way for us to determine that those vectors are in fact parallel. So if you actually took the vector that went over 6 up 8, which is a multiple of the first vector by 2, of course, that vector 6, 8 falls right on top of that. So if I pulled that away from that vector, if I pulled the vector 6, 8 away from this one, which is the vector 3, 4, they would actually still be parallel to one another, even though the one superimposed and fell right onto the other one. So let's talk a little bit further about something like a vector's length stroke magnitude. You see each of these words as descriptors used synonymously. And so if you're over 3 up 4, not surprising by virtue of forming a 3, 4, 5 right triangle that the length of this vector OA, which is what's being communicated by these sort of absolute value looking notational form, that ends up giving you that the length or magnitude of A is 5. So just a glorified version of A squared plus B squared equaling C squared, with just looking a bit more abstract because of conventional vector notation. And then, of course, vectors not only are two-dimensional in the sense that they have length, but they also have direction. And so that direction would be related to that angle there, which is with respect to the horizontal here. And of course, the tangent of that angle, which would be opposite to adjacent, would be 4 over 3. And so if needed, the angle of 53.1 degrees describes that vector's direction. Let's start to move into a setting where we'll not only see how some trigonometry can play a role at times, but then in the second podcast to follow, we'll see another vector means to get this same answer of 133 degrees. And so if I give you two position vectors, namely OA, which is at 3, 4, as we previously saw, and here's a new vector OB, so go over 12, go up 5, and that's the way to actually get yourself from O to B. So those two position vectors end up allowing you to say, okay, there's a third side or a third vector that could be formed, namely getting from A to B. Well, getting from A to B says go over 9 because you're previously at 3 versus being at 12 here. So going over 9 while at the same time you're going up 1. All right. So you can actually count in space, right? Going from 3 to 12 is just 9. Going from the y of 4 to a y of 5 is obviously 1. There's a better way that can be accomplished in terms of going from A to B. You can go firstly from A to O and then add from O to B. So it's kind of like taking a walk from here to here in terms of getting from one place to the other is the same as walking from here to here and then add the walk from there to there. So not necessarily needed in two-dimensional space as a method for coming up with AB, but very much will be needed in three-dimensional space, and we'll see that in a few minutes. So again, A to O plus O to B, that's the way you're bridging from A, starting point is at A, to the point of B. So to get from A to B, you're going to bridge through O. Well, we already saw that the vector AO is the opposite of vector OA, so hence negate it, and then here's your -3 plus your 12 being 9, here's your -4 plus your 5 being 1. And then if we needed it, and we will in a few seconds, the length of this vector AB is no more than just, like if you can envision there's a right triangle in there, so going over horizontally, as it turns out, 9, up 1, and there'd be a right angle formed there, so that 9, 1 hypotenuse thing will give you that the length of that vector, which is essentially that hypotenuse, is going to be the square root of 82. So the context for that will be, let's actually talk about this sort of triangular construct now. We've got some angle in here that I've labeled as theta. Our goal is going to be to find theta. We do know from OA, so classically 3, 4, 5 in terms of the length of that vector being 5. And then OB, if you recognize there's such a thing as a 5, 12, 13 right triangle. So go over 12, go up 5, then the hypotenuse of that will be 13. And so as it turns out, we've got a triangle here. We've got 3 lengths of the sides of the triangle. And if we're trying to find that particular, what looks like an obtuse angle right there, then a good old friendly law of cosines can kick in, because we know that sort of this is a challenging looking vector version of it, but you might recall that c squared, if that's my length c and it's across from my angle c, so if that's my c squared, that's going to be the cosine of the angle opposite, which would be cosine of c, and then you've got sort of c squared equaling a squared plus b squared minus 2ab cosine c. That's classically law of cosines. It just looks a bit more menacing in vector notational form. And so here it is represented up here nicely for you. Again, that length of 13 is across from the angle that we're trying to find. That's classic law of cosine stuff. And so this whole negative term, I've added it over to the left. That's why it's here positive. And I've subtracted the 13 squared. That's why it's here negated. And then when you do the actual work on this, carefully do the arithmetic, you would end up getting that the angle in question is cosine inverse of this rather menacing looking form, which you would find to be 133 degrees. And again, we will be revisiting this in a pure vector setting sometime soon. Let's start to venture into 3D, where we've got the x, y axis traditionally, and then going in and out, you've got this z axis to form three-dimensional space. And so a point like 2, 4, 3 would say go over 2, go up 4, come out 3, and that would allow you to talk about vector OA, which kind of has this representational form, and then that point B, which says go over -1, go over -1, drop down 2, come out 5. Hard to start to conceptualize this on a two-dimensional piece of surface versus the fact that it's really 3D. That would give you that vector, namely OB. And so coming up with vector AB, which you can no longer do with the sort of over 9 up 1 thing that we saw previously. Now you can say, how do you get from A to B? Well, you start at A and you bridge through O to get to B. So you can see going from A to B is accomplished by linking through O. And you have both of those as your position vectors to help you do the construction. So what is vector AO? Well, obviously it's the negative or opposite of this vector, hence the negative of that vector OA, which is giving you vector AO, plus the OB. So -2 plus -1 is -3. Here's your -4 plus -2 is -6. You get the idea. So wherever A and B are in space, without doing somehow a miraculous left, right, up, down, in, out count, you can say, well, B's position, right, its head relative to A's tail is what you see represented there. Couple of quick confirmations. The distance formula, which we should be familiar with, difference between the x's squared plus difference between the y's squared, the square root of that, that's classically distance formula, which is basically based on sort of a squared plus b squared equals d squared, you know, in terms of Pythagoras. It's going to extend into 3 space by just rather elegantly adding in a third dimensional component there. So that's just something to keep your eye on as we proceed. And where that could be useful would be twofold. You've got something like given 2 points in space, finding the length or distance between those 2 points, you can simply say the difference between the x's squared, here it is right here, plus the difference between the y's squared, plus the difference between the z's squared, ends up giving you the square root of 49, hence 7. Well, we already just saw in the previous panel that we can construct vector AB by working AO plus OB. Here's vector AB, we saw it previously, and as it turns out, the length of a vector is no more than just the square root of the squared components of each of these 3 x, y, z components, and you get the same value of 7. So a final example dealing with some unknown vector v, which has a coefficient in terms of the unit vector j that's unknown. So let's actually find n, given that we do know that the length of the vector is 3n, where n's qualified to be some real number. So the length of a vector, once again, is just going to be the square root of the x squared plus y squared plus z squared. That's pretty straightforward. Just extract them out. You know, these I, j, and k forms are a bit superfluous. You can just look at the -2 and 6 in a column vector form. So adding up the squares of those and setting it equal to the length that it needs to be. Classically, a radical equation, square both sides. The square of a square root effectively drops it. And then here's your 4 plus 36 being 40. And here's n squared. Bring this guy over. 8n squared is 40. Divide by 8, and you've got plus or minus root 5 to be the final result there. Okay, that was round 1. That's it. Thank you.